Okay, well, welcome to section one of our quantitative research technique, talking about statistics and understanding what statistics are. Again, a lot of times statistics, if this is your first course in it, it can be overwhelming. It seems like everything is new and confusing, and on some level, that's probably the hardest part for most people because it's new. And it's this combination of new terms and math together. It seems like it's overwhelming. But I want to encourage you as you start your journey in this section and dealing with statistics. I want you to understand that the mathematical calculations are well within your wheelhouse of being able to do these. Everything that we're going to do in here, we're going to use a lot of square roots and exponents and things like that. But ultimately, right, everything comes down to adding, subtracting, multiplying, dividing. So don't get overwhelmed with some of the math. We'll try to break everything down for you. The terms is really what I'm going to need your help with. I need you to really engage and try to learn some of these new terms and understand exactly what they mean. And that's going to help you along the way as we encounter, because we're going to learn things in this section here that we're going to use throughout the rest of it. And so if you don't pick it up now, it's going to be a problem. You're going to have to go back and kind of relearn those things. So statistics, again, looking at numerical facts, we have different ways that we want to describe things. It's called descriptive statistics. But we think about statistics as the averages, as percentiles. Um, it's really an art and a science. There is no math is set, right? 2 plus 2 is always going to equal 4. Statistics is about probabilities, is about the likelihood of events occurring. And so it's not always a set thing. There really is some art to this whole thing, especially when we talk about analyzing, presenting, interpreting the data. You and I can look at the same group of data and come up with a different interpretation of it. Is the data wrong? Is it inaccurate? No, it's just you bring a perspective and I bring a perspective to data that would be different. And so just keep that in mind. Statistics really does help us provide meaning to data. Here we got a group of numbers that mean absolutely nothing to us. If I said, look at these numbers and tell me what you think, well, I don't think a whole lot. I think it's a group of numbers. But statistics allow us to apply calculations and describe the data that makes it meaningful. Again, we talked in the technology section about humans are the only individuals that are able to provide meaning to information. So we go from data to information and then meaning, right? And we apply that meaning ourselves. So if you think about it, statistics is used in absolutely every corner of business that I can think of. Actually, I can't think of any industry area that doesn't look at statistics. When I look at the church I attend, right, they're trying to figure out how many people are coming, how fast are they growing, what kind of needs will they have in the future, what does the weekly offering look like. Nonprofits use statistics all the time, right? You use statistics, you probably didn't even know it. What's your miles, the average miles per gallon in your car when you're driving to work? How long is it going to take you on average to get from your house to your job, right? All of those things are, in essence, statistics. Um, Now, we think of statistics as like this heavy quantitative stuff, but again, it's so enveloped in our lives that we don't really recognize that we are using statistics because it does simply is incorporated in every area that we can operate in here, especially in business. Descriptive statistics are just as the name implies, they are descriptive. They are used to describe the data. So if I were to say, hey, the average height of males in the U.S. is 5'11", right? I've literally just described the data. I've used one point, one measurement, the average, and I've described the data. And so there's a lot of different ways in which we can use to describe the data. One, I can give a number, or I can give graphs, right? I can show you histograms and bar charts and box charts and stem and leaf and all these different ways to describe the data. But what I'm trying to do ultimately, whenever I'm describing data, is I'm trying to convey information. So if I'm spouting off a whole bunch of numbers and that's describing the data, but no one else is getting it, I need to use something else, right? My point is that I should be able to convey information through descriptive statistics. The biggest areas, numerical measures that we look at are these four different categories here. We've got location, dispersion, shape, and association. So location is the mean, the median, the mode, percentiles, quartiles. Where are all of the numbers most likely grouped together? What is the typical number that we would get? Again, if we go back to the male, the average height of males in the US is 5'11". Well, the average height would be the 5'11", right? That's where the largest grouping of individuals, if you were to measure folks, measured every male in the U.S., they would all be about that 5'11" mark. Okay, dispersion is talking about how far spread apart the data is from each other. What is the here you see range, interquartile range, variance, standard deviation, and coefficient of variation. These are measures of how far spread out the data is. What's the highest and lowest? That's the range, right? The standard deviation is what is the standard measure from the average. And again, that standard deviation is going to come back for us. We're going to learn how to figure out standard deviations. We're going to figure out variances and all those things. The shape lets us understand, hey, is this relatively symmetrical? Are the two sides, data points above the average and below the average, do they look about the same? Is there more data points on the left-hand side of the average or the right-hand side of the average if you're thinking about a graph, okay? And then finally, association is looking for any kind of correlation or movement or similar dispersion between variables that's going on, okay? How are they related to one another, all right? So those are our four kind of categories that we can use descriptive statistics. So let's look at an example. We've got an automotive company here. They do automotive repairs, and to better understand the cost of the parts used to perform engine tune-ups, the owner would like to examine 50 customer invoices for tune-ups. And then, based upon those costs, she can run an advertisement, right? Or she can work with her suppliers to reduce those costs, or she can work on her labor to figure out how do we do this more effectively, right? Or she can give better estimates. Now, if I know what my average cost is, and someone calls on the phone, I can say, well, listen, most tune-ups on average are going to cost about X, right? So we're going to use data, this grouping here of 50 tune-ups, and we're going to try to turn that into information that we can actually use, okay? And so one way to do that is we can do a frequency or percent frequency distribution. Again, this is a table to lay out the information, try to describe it better. So the way this works is simply saying, okay, I'm going to look at one grouping of information here. I've got from $50 to $59. I've got two tune-ups that cost that, and when I add up all of these, I take my 2, divide it by 50, and I get 4%. Okay. And then I moved down in the next bin from $60 to $69, right? I had 13 tune-ups that costed that. I take 13 divided by 50, I get 26%. When I add all of these percentages up, should come up with 100. And when I add up all of these frequencies, I should start with that original data point that I had, those 50 that I have here. You'll notice too, I want you to draw attention, the difference between, this is called the class width. The width of these classes here is 10. Even though it says 50 to 59, it is not 9, right? Because it's 50 is included, so 50, 51, 52, 53, 54, 55, 56, 57, 58, 59. That is 10. And the way I look at this, and the way I want you to look at this, is to look at the distance between the classes. So from 50 to 60, that's 10, right? So keep that in mind as you're looking at these tables and frequency distributions, okay? So here it is graphically. This is the exact same information that we had in a table format. Now we simply have it graphically. And when I'm visually looking at this, I'm like, wow, okay, it's pretty obvious that the average tune-up is between $70 and $79 based upon this histogram is what we're looking at here. It's not a bar chart. The fundamental difference is that there are spaces between bar charts. On a histogram, they are continuous, okay? Boy, that sounds like a nitpicky thing, but nonetheless, that is how you distinguish a bar chart from a histogram. So, one of the things that is important is after we've described the data, we might want to make inferences on it. So statistical inference. So those are really the two categories: descriptive statistics and inferential statistics. Okay. When we look at inferential statistics, we want to understand what it is about a population, those characteristics, and then can we infer things from our sample? So we had 50 sample tune-ups here. Can we then take that information and infer that the population is the same? What if we took those 50 samples in a week where we only did tune-ups on imported vehicles, or we only did tune-ups on classical cars because there was a classical car show in town that week, and so we took our samples. Could we then infer that that is what the actual costs are in the entire population? Probably not. It'd be skewed a little bit here. Okay, so those are some of the things that we have to keep in mind when we're talking about looking at a population and making inferences from a sample onto a population. All right, so again, population is all the set of elements of interest in a particular study. I'm using the word population here, and I'm not talking about people, right? I am talking about all things that are in essence possible. So if I wanted to, I could easily say, listen, the population for um, this factory or all the widgets that it produced. Okay, that's a population, not people, but it could be things. In the tune-up example here, it's all of the tune-ups that we've ever done. That's our entire population, or it could be a population for just this year. How many tune-ups did we do? That's our entire population, and we're pulling a sample of 50 of those. Okay, so from the population, we pull a subset, which is our sample. We do a whole bunch of data, statistics on that sample, and we get things like the average, standard deviation, dispersion, the shape, right? All of those things. And then we're able to, in essence, infer that the population has the same descriptive statistics as our sample. Right, and there's something called confidence and significance level we're going to talk about today as well that will also play a part in this. So when we do a census, we collect the data from the entire population. Here in the US, that happens every 10 years. The reason we don't do it more often than that is because it is costly. And oh, by the way, that's exactly why we use a lot of sample data, because collecting the entire population is extremely time consuming and costly. Okay, so whenever we're looking for um, quick, easy numbers, not bad numbers, but quick and easy, we need to take a sample. We need to take a sample. All right. Okay. So it is important that you understand how the direction works. From a population, we get a sample. We get a subset from the population. We run the statistics on that subset. Okay. So here we've got population. From our population, we grab out a sample. From the sample, we get statistics. We infer those statistics about the population. And anytime we're working with it, the population has parameters and the sample has statistics. So what does that mean? That simply means that as we look at the sample average would be called a statistic. The population average is a parameter. The sample standard deviation is a statistic. The population standard deviation is a parameter. Okay, so statistics belong to samples and parameters belong to populations. All right. A couple other things to let you know when you are working with a population versus a sample. One is the lettering, the notation that you'll see. So for example, let's look at the mean. The mean is the average, is what you think of the average. And for a population parameter, it's denoted as the Greek symbol mu. Mu, okay? For the sample statistic, it is our X bar, our X bar. All of our population parameters have Greek notations. All of our population parameters have Greek notations. Sample statistics are our typical lettering that you and I are used to. Actually, they're Roman letters, as it turns out. Okay, so Greek is population parameters. Roman letters are sample statistics. Okay, that should help you as you are reading through any kind of journals or technical information, statistical information. If you are given Greek letters, they are speaking specifically about a population parameter. All right. So in this case, our population consists of all the tune-ups. The average cost of the parts are unknown. We don't know what that average is. We didn't take a census of all of our tune-up costs, but we took a sample. So we pulled out 50 engine tune-ups. The sample data provided the sample average parts cost of $79 per tune-up, which corresponds exactly with what we saw in our histogram on the chart. And then based upon that sample average, we use that to estimate or to infer that the population tune-up average is also $79. Okay. Hopefully that makes sense how we got there. All right. Um, a couple of concepts here: data warehousing within, again, as we talked about in technology section, being able to capture this data, being able to use it, access it readily is pretty important. It's estimated that Walmart captures about 20 to 30 million transactions per day. You can imagine, Amazon, Facebook, the number of images, the amount of information that's created on a daily basis with pictures and everything else that gets on Facebook, and is just astounding and staggering. So being able to store this stuff is pretty important. And then being able to mine through it, right? What good is it to have it and store it if we can't use it? If we cannot turn all of that data into information, and then where you and I can actually apply meaning to that information, okay? So it's a process of storing, combing through it, data mining, and then being able to produce information and meaning from it. Obviously, there are all kinds of ethical guidelines that I would love for you guys to consider. Sampling practices where we look at certain individuals. We're only asking questions and taking surveys of individuals that may not represent the entire population. Um, in the world in which I live, with a lot of statistics and finance going on, there's a lot of questionable things that are happening. But again, it's really about the individual biased. Some I'll call it your point of view, okay, is a nice way, but really it's our bias that we bring to the table when we're looking at data. So just keep in mind, I would ask you to question everything. You should question every statistic that you run across and say, does this make sense? Does it make logical sense? Not saying that statistics are always logical, but I am saying that you should ask the question and don't take anything just at face value. Okay, that would be my encouragement for you. Some pretty prominent examples of statistical misuse are out there. Again, even as recent as some of the election results here locally and in our nation, again, there's some issues. So this is my favorite one, though. I want you guys to think about this for a second. The percent of marriages that end in divorce. Growing up and going to church, I heard this all the time. These are the reasons that the U.S. is failing, is that the family is breaking apart. Everyone knows that 50% of all marriages end in divorce. Well, that statistic is actually incorrect. As a matter of fact, what had happened was they asked the people, I think they asked them a question and said, hey, how many people got divorced in, for example, 1995? And they had that number, and then how many people got married in 1995? Well, they looked at it, and the number of people who got married, the number of people divorced were exactly half. Therefore, 50% of all marriages end in divorce. That's a bad statistic. As a matter of fact, everything that I can see so far is that the divorce rate is actually declining in the U.S., right? Well, that should hopefully lead you to another question. Are people getting married as often? Is there as many marriages? And so there's a lot more questions than simply 50% of all marriages end in divorce. That statistic is incorrect. It's nowhere near that here in the U.S., okay? Um, Okay, so just a quick recap here. Statistics can either be descriptive or inferential. We can use descriptive statistics on both populations and samples. When we look at inferential statistics, again, we are using the sample statistic and we are inferring that onto the population parameter. Okay, so kind of some nuances and terms, but I'd love for you guys to know and understand those. All right. The last thing I want to talk about is the understanding of confidence and significance levels. Confidence level is how accurately your sample represents your population. A lot of times you'll hear, and as we move through this course, we are 95% confident means that you will get the same results 95% of the time, even with a different population sample. Okay, so it's almost like saying if I were to run this sample descriptive statistic of an average, I pulled a sample of 50 tune-ups, I got an average of $79. If I'm 95% confident, I could pull another 50 sample, I could find the average there, and I could get 79. And I could do it over and over and over and over again. In essence, 95% of the time, I'm going to get a population average that is similar to the one that I've just gotten. Okay? And so the opposite of confidence level is, I shouldn't say the opposite, a level of significance, the level of significance. So significance level measures how frequently the conclusion will be wrong, which is our level of alpha. And our confidence level is, in essence, how often we'll be correct. So when I add up the confidence plus the significance, I should always equal 1. All right. How often we'll be right plus how often we'll be wrong should equal 100% of the time. There is no maybe category. So confidence level plus significance level equals 1, right? And we will always use alpha to represent the significance, and our confidence level will be 1 minus alpha. 1 minus alpha. So take note of those things. That is it for this section. I will talk to you guys in the next one.